we're not going to go on too much longer and stuff because I want to leave a lot of time at the end for questions and just my advice for if you guys actually want to get more in-depth experience and the resources that you can look at afterwards, because I think that's a really important part of this. I don't want you guys just to come to this and then this be the only resource that you have. And if you actually genuinely are interested in it, I'll share a few things that really helped me learn all of this and the resources I recommend for people. But yeah, we'll just dive back into this. We're about halfway through the file. Just getting to the fun stuff. Everything's been pretty boring to this point. So I'm showing off here. Geez, this just seems so boring to dive into, describing the data. But the point I want to highlight here is Pandas actually has a ton of really nice built-in functions to get an idea of your data. So if you do this describe, you can see the standard deviation of each different feature that you have. You can see the count of records. This is obviously going to be the same for all of them. But if I had ran this before when I had null fields, you'd be able to see how many of them actually had null values. Mean, max, different things that maybe have a lot of relevance. So if you run this .head command, you can actually, just like if you're running head in your terminal, get just the top few records instead of everything, which can be pretty nice just to have an idea of the columns and what the data looks like. And then this last thing's pretty cool. I don't use these a lot, but I should sometimes. If you're just trying to get a preliminary idea of your data, trends, things like that, you can do this df.hist and just put the size. And in line, this is some of the plotting you can do where we'll actually plot a different histogram for each of the different columns. So you can see where your data is more weighed. So you can see for the passenger class, most of it is that third class. You can see for age, kind of like where people's average age is, that there's a lot of people in their 20s and 30s. A lot less people like in their 80s. There's almost no one on here. So it's just really cool that in one command, you can do this histogram for all of those, I think. And then you can see the balance between your data sets. So this is the number of people that didn't survive. It's just so morbid. And this is the number of people that did survive. So you can see it's a pretty even class. It's not like we just have a little shred for the number that survived. So now we're on to the training. So this is the most exciting part for sure. And I had a really great question before that I just want to bring up. If Python is not your thing, if any of you know R is the other like prominent data science language, and you can actually switch in Jupyter to use R and all, but still do this cell style of programming instead of just using Python. So that's what makes Jupyter such a nice flexible tool.
How about .NET?
So there's some frameworks for .NET, but you cannot use it. I know this is the .NET meetup, but I have not ever used .NET for machine learning. But so in here is where I talked about the splitting of data. So this is the first step you want to do. So I'm going to, from SciKit-Learn, which is our machine learning library with just every goodie that we could imagine in it, we're going to, you don't necessarily have to remember this. I normally have to Google what it is because I won't know what the next extension is. But I'm going to import the function train test split. Now I'm going to do that X and Y that I was talking about. So X is all of our input features and our Y is our target output. So all I have to do is make Y equal our df survived column. You can actually also, it's really weird, you can do dot survived if you want to, and it will do the exact same thing. And then I want to get my X, and it's going to be the data frame, but I'm going to drop the survived column. But you can do this all in the same line. You don't have to set the data frame to that because we want everything except for the output column. And then after that, we're going to do our train test split, where I'm going to take the resulting variables I get to set are x train, x test, y train, y test. So when you do this train test split, I'm putting the x in, I'm putting the y in. Test size is going to be 20%, and then the random state can be whatever your favorite number is. And then once you run that, you'll get a really nice little split. So I can actually, I'll insert a cell below, and we can look at the length then of our, actually we'll look at the shape. So now if I do xtrain.shape, it'll just give us the shape of the matrice, and I'll do xtest.shape. So you can see, for this is how many input columns we actually have. So we have 7 different columns that we're putting in. And then for our training, we have 569 different examples we're going to train it on now. And then for our test set, this is what we're going to evaluate on after. We have 143 different examples that it's never seen that we basically want to evaluate it on. And then the way you can associate basically something from the X and the Y is if you go to your X train and you look at index 0, and then you do your Y train and you look at index 0. Oh, what did I do wrong? X train, Y train. What? Hoping nothing would go wrong. Should have stuck to the code that I had in there. There we go. So basically this is our Y train. So this is all of the labels for each thing. So if I look at index 0 here, which would be this 1, that would correspond with the X train index 0. Oh, I think I know what it is.
What is this random state?
Random state is what I was talking about before, where we basically are seeding the random number generator so that it's reproducible every time. So it will randomly shuffle it for this first time, but it seeds it with this. So every time we then do the split with the same random state, it will be the same slice of data every time. So you can change it a few times, but it's where you don't want to have it change, like randomly pick a new one every time, because it might be a different quality data set. So then if you're trying to optimize your algorithm, but you keep doing different splits of data, that will also impact your accuracy if you keep changing the split. So you want to make sure it's the same split every time, even though this is a random split that will now be the same every time because we've seeded it, just because then we can reproduce our results.
How do you pick up 42?
I don't know, I just see it in a lot of people's code. Isn't there, I feel like there's that one reference that the number of the universe or something is, the key to the universe is 42. So I see a lot of those like data scientists hide a lot of those fun little things in here, but it doesn't really matter what number you use.
Can I use 1 million?
You can use 1 million if you want. I don't think it affects anything, but let me see. Oh, still didn't fix that. That's okay. So this is the split. Does everyone understand the splitting? Does that kind of make sense? We want to just save 20% of our data to test it on that it hasn't seen, so we can actually see how it will perform on new data instead of just the specific stuff that it's seen. So now, here it is. And this whole code block will train a whole machine learning algorithm. Again, I should have erased the output, so it's a little more of a surprise. But so from Scikit-Learn, and we're going to take a linear model, we're going to import, this is one of the most basic ones, it's called linear regression. So we're just importing it just like any other library that we would. We're now going to just set any variable that we want to an instance of it. So I'm going to just do, for this, I'm just shorting it to logistic regression underscore classifier. But you can name it whatever you want. A lot of people just do CLF. I'm just doing this because we're playing with a few of them. And then you just want to create a new instance of logistic regression. Now, all you have to do is this .fit command, and this is where we'll train it, basically. So we give it our X train and our Y train. So this is the input, and this is the target output. So it will keep going through all this test. It will do predictions, and it will then compare its prediction to the output. If it gets it wrong, it will keep going back until it's corrected itself and understood the pattern in the data. So then after that, maybe I'll split this up so it's not so much at once. So if I run that, it's now, oh, what is going on? Did I not drop something? So, this is a great example of why these numbers are really valuable. So you can see I ran this code and it has the 9 here, but I actually forgot to run this code right here as the 23, so it was run afterwards. So even though it has the output, this was from my last run from before, so I just have to rerun this again, and now it actually dropped the embarked and created this. If I had printed our data frame, I should have done that. It actually hadn't ran that code. But you can see now we have 14, so now if I run anything after that, it will be higher than 14. So if I run like this, I'll just dive down here. If I do the split again, you can see it's 15 here. So that's why none of my stuff was working before. So now we're here, we're gonna run this again, and that's all we have to do. And now it's trained a linear regression classifier on our training data. So a lot of these traditional algorithms in here train a lot faster than, a lot of you have probably heard of deep learning, which is this new subset of machine learning that's really promising. Those models take a really long time to train as opposed to these ones that just know the different steps and calculations they'll perform every time. And then you can see, because I have this as the last thing in my data frame, it also just like dumps the object. But it can be really useful because I can actually see all of the different parameters that this algorithm has. And then if I did want to go and change a parameter, I could just copy this. Then when I create it, I can just put them in here. And now I've trained it with a new different parameter. So that's a great way that without you having to Google, you can see the parameters for an algorithm. Just create an instance of it, then put it as your last thing in a cell. So if I just had done this as well, it would still print those. So we're going to go back to the dot fit. So again, that's all we have to do to train. And now, oops, I deleted my code that we needed before, but I'll just copy this. I'll just write it from scratch. So now what we want to do is our predictions. So this is really easy to do as well. So I'm going to create a new array basically called predictions or preds. And now if I do this LR underscore CLF, so this is our trained classifier, or trained model, trained machine learning algorithm. I'm going to do dot, and I want to do predict. So I'm going to give it just the X test. So remember, this is the data that it hasn't seen before, and it's actually going to do a prediction for each entry in this. And if I put preds as the last, so you can see this is the predictions that it's done. Now some of these algorithms, you'll see they actually give you a confidence score or one of these scores instead of actually giving you just like number of 0 or 1. So a really easy way to fix that is if I do this np dot, it's basically round int, so we'll round to the nearest integer. It's nice and clean 0s and 1s now. So that's all you have to do when you get an output like that. So I'm going to now set our preds to be these rounded ones. Oh, forgot the equal. So now, final thing, this is the most exciting thing for sure, is I don't know if I imported it yet, but I'm going to go from SciKit-Learn dot and metrics, import. And now with this, because we're doing classification, we can use accuracy score as a nice metric for this. So now all that I have to do to actually see the accuracy score, so it's really easy. It's going to take all those predictions and it's going to compare it to all the Y test values. So the Y test are the values we know are right for the X test. But if we compare those Y test values to our predictions, we can know how many of them it got right and get a percentage score. So all I have to do is do this accuracy score, predictions, Y test. Now if I run it, that's all you have to do. And you can see with 77% accuracy, we can actually predict if someone's going to survive on the Titanic or not. So this is a really great baseline, and it's a really cool example because it shows that there was clear correlations and trends on the ship of who survived and not. And if you think about it, it's really easy to imagine that they prioritize kids and mothers, so there's actually a real trend. And then if you were older, that there'd actually be more of a trend of you not surviving because you might have stayed in your cabin, something like that. So it's great now that we have a baseline where if this was 10 or 20%, we might question if they're even if it was only 30 or 40%, we might question if there even is a trend that we can analyze, but this shows as a baseline that there actually is. So now, I want to show how easy it is to actually change classifiers or algorithms in Scikit-Learn. So now here, it's almost the exact same, but I'm going to do from SciKit-Learn Ensemble, it's a different type of machine learning algorithms, a random forest classifier. So this is one of my favorites. It serves as a great baseline, and what it is if you can imagine a decision tree where you'd say like, if age under 30, go this way, if not the other way. A random forest will plant thousands of decision trees, they're called, but randomly. So it will make thousands of small decision trees, and then it will compare the results of all of them, and it's almost, it's like a voting thing. So if most decision trees agree or have this output, it will then do that. So it's a really fun little algorithm to use, and it actually performs really well in the wild. So then all I'm doing is now creating a new instance of it. So RFC, I'm naming it. Almost the exact same as if we go to the linear regression model here. So RFC, I'm just creating a random forest classifier. We'll just do it with the default parameters first. I'm doing the RFC.fit. I'm going to do it with the X train and Y train again. Exact same syntax as before, other than I'm doing it with a different one. And then for the preds, exact same again. So it's all really identical code, other than we've only really changed that we're just using a random forest classifier. So now if I run this again, you can see just like that, 81% accuracy without changing any parameters, doing any additional tweaking. So this is a great, even better default score. So then my next steps from this would be, I would basically, I'm going to take this bit out, and I'll just put in a cell below. So now if I run again, And like I said before, if this is the RFC.fit, or if I just did RFC as the last object in here, it would show me the default parameters it has. So this is where you can actually see different parameters you might want to change. So maybe I want to change the number of estimators, and let's make it like 200, just a crazy number. So I'll run that, and you can see it's been changed. So now I'm going to do predictions with it. So you can see it actually dropped quite a bit. I'm at 76% now just from tweaking one parameter. So this is where it gets to be really fun and challenging to actually see which parameters influence it in a positive way as opposed to negative way. So one way of doing this would be just manually setting these every time. So I'm going to go back to the default. Oh, the other thing I should have mentioned, just like our training test split, actually this is a really great example. So any algorithm that has an element of randomness, you can also set a random state in. So just like when we split our data, you can reproduce the algorithm's results, because you can see now if I create a new instance of this, something in it has had some random number generation. So now if I run the prediction again, it jumped to 74, and we haven't changed anything at all. So this means that it's really hard to evaluate which metrics here basically are affecting our thing, because we're getting a different score anyways. So just like when we do our test, the train test split, I can actually set random state here. I'll do it to 42 again. So now if I do this and I keep running it, we got 79, I'll run it again, keep running it, you can see we can actually reproduce our results. So whatever was our random thing before, we've now seeded, so we'll be the same. It still has an element of randomness, but we've just set it to be the same random number each time. So again, now if I change this to be a different seed, we'll get a different output, just like that. So now if I go back to 42 though, we're back to seeding it the same. So it's really important, if your algorithm has some element of randomness in it, it generates some random numbers, like a random. It's easy to tell with a random forest, but some other algorithms you don't necessarily know unless you keep rerunning it and see it just randomly changes without you tuning anything. It probably has a random state, and you'll want to set that just so you know when you're actually changing your other parameters how impactful it is. So now another really cool thing, so this might actually influence you to go back to that pre-processing and feature engineering step. Once you've trained an algorithm, you can actually see the feature affordances. So this is when it looks at all the features and looks at how it's making its decisions, which ones actually have more of a factor in it. Whoops. Oh, why is this happening? Oh. Sorry, when I thought I was fixing something else, I messed it up down here. So if you do this dot values, it turns it just to a 2D array and gets rid of the headings, but that for loop that we just had actually needs those columns. So here we are. So with any algorithm that you train, they'll each view things a little bit differently. For example, I'm going to take this and I'll actually do this exact same thing, but for a linear regression classifier that we had as well, or logistic regression. Oh, just kidding. I guess lr.clf does not have the feature affordances. Just kidding. So we're going to delete that. So different algorithms will have this feature and won't, but random forests are great because you actually can see what it makes its decisions on. So you can see age, that was 20% of its, a 20% factor in why it made its decisions. Same with gender or male for this, that was 28%. So you can see now if we look at our embarked, the C was 1%, the rest were less than 1%. So we could actually now go back and say, it's probably pretty safe to drop that embarked column altogether. Like if it's a 1% difference, it might actually be causing more harm because it might be trying to draw a relationship between those. So it's kind of cool though to train an initial baseline model and then see how a machine learning algorithm is making its predictions. Because now we could say, well, with 70 or 79% accuracy, if we just made a decision based on fair, male, and age, that's over 80% of how it's making its decision is just on those 3 columns. So we see what's actually important to it and what is just helps it a little bit. So to wrap things up, we're almost done this code, and then I want to go over a few of those great learning resources. But where I was talking about just changing the different parameters, instead of you manually going back and changing like where we changed it from 20 to 200 and back, this is where you can do a grid search is one way. So you can see I'm making this parameter grid here where the number of estimators, and I'm going to give an array of different options it might be. Same with the max features. So these are the different options it has for this max features one. For each different algorithm, they have different parameters. So you just need to look it up, its documentation, and see what its parameters are. There's no way of knowing off the top of your head by any means what are the parameters of an algorithm, or you'd just be able to jump in or between them all. So I'm setting this parameter grid. I'm making this new thing called a cross-validated random forest classifier. So I'm using this grid search CV. My estimator is my random forest that I'm creating right here. My param grid is just going to be this parameter grid dictionary that I made. And then this CV is a pretty cool feature here. So it's called cross-validation. So where I was talking about you set a random state for your training and test split, sometimes you won't get the best split. Maybe all of your outliers are in your test set, so your algorithm isn't actually trained on them. What the CV parameter does is it actually will retrain your algorithm 3 different times with 3 different random splits of data. And then it will take the average score between those 3. So just in case you get a bad split the one time, you'll get a more accurate score. So it's a cool thing you can also do in here. So now what this, all this code will do is it will actually do every single combination of these parameters. So we'll do 20 in auto, 20 in square root, 20 in log 2, 25 in auto, all that. And it will train each of those specific ones 3 times. So at the end of running this code, it will actually train 3 times 4 times 3. So we'll train 36 different algorithms to find the optimal parameters. So I'm just going to run this. Just ignore these deprecated errors. It still lets you run everything. So it can take a little longer. So it ran pretty fast because we didn't add any, but you can imagine this is like logarithmic growth when you add another possible candidate here. But now you can see here, if we look at the, where is it? Now if we do CV underscore RFC, so that's our classifier that we just trained, and we do best estimator, it will actually print the best parameters that it found training all those combinations. Now if we wanted to create a new algorithm, we'll go back up to our original random forest. I can actually put all of these parameters, just copy and paste them into here. Random state is still there. So I've trained it. Oh, and it didn't perform any better. But you can see that that will be the best combination for all of those possible ones it did. So this is just one example of how you can actually do different like parameter sweeps and find different combinations of optimizing an algorithm. But what I find really valuable is just there's tons of algorithms, try a few of them, look at the ones that are the most promising, then start tweaking the parameters a bit, see from those which ones are you're getting more noticeable gains from just doing tweaks, and then try doing a different parameter sweep of them to find them. And then at the end of it, it's really nice because you just get your algorithm, and then you can do anything you want, predictions, put in the value you want. And yeah, this is kind of a start to finish, code-wise, of doing a simple supervised machine learning problem. I think that it's a really nice, the Titanic one is a really great example just because you go over the making that truth table, you go over having to make the male or the gender thing to be a male, true or false. You drop columns that are relevant. So I don't think it's a fun data set, but I think it's a really great one because it goes over every case that I think we'd want to handle. And I hope that I haven't gone too fast for you guys because normally we would do this in like a full day at work. So this was definitely a sped up version of it. But now the important thing is, I think, for you guys, if you actually do want to further your career, you actually want to play a lot more with data science, this is just a simple stepping stone. And I try to show how easy it can be. And then same with this code here. I actually have this other, the nice thing is in all this junk here, you can see the other things that I have. For examples, it's not that one. I'm going to go to this end-to-end housing. So this is another great one where you can take a lot of this code. Oh, there we go. You can take a lot of this code and actually copy and paste it and just load in a different data set. And a lot of the same great tweaks you did for one data set will actually transfer to be something completely different. So we were predicting if someone survives on the Titanic or not. We could take most of that code and then predict with a great deal of accuracy if someone has diabetes or not with a different data set. So just like that, we can transfer all the tuning that we did. So it's really cool. So I try to include a lot of simple readable code in here so you can actually go and copy and paste it and play with it a little bit if you want. So the next thing that I think is important is, yeah, the resources that I like the best. So there's this book. I normally hate textbooks. Whoops. But O'Reilly publishes these amazing books where they're a lot more readable and less focused on the math in the background. So this O'Reilly book called Hands-On Machine Learning with SciKit-Learn and TensorFlow, I find to be just a gem of a resource. It's amazing. The second chapter, they go through an end-to-end problem from start to finish in a lot more detail than I did in this short time. At the end of every chapter, they have sample code you can do and play with examples. And they actually, a lot of these O'Reilly books for data science do this. They make a GitHub repository where every single code sample for every chapter that they have, they'll make one of these notebooks like we just looked at. So you can actually open the notebooks and look at the exact code that they do in the book and tweak it and play with it as you're reading it. So it's a really great resource to be able to go back and forth from reading to something more interactive. And instead of having to write a big sequential piece, this is really nice having descriptions with it where they kind of explain what they're doing, different steps of the way. They do a lot more complicated plotting than we do. But it's cool because this is all usable code that you can copy and usually use in different cases. So if any of you are interested, I recommend getting this book. It's pretty cheap. It's like 30 bucks. It's not like a real textbook, so it's just an amazing resource. But I only recommend if you just want to get a base for machine learning, the first half is all you really need. The TensorFlow stuff, unless you want to get into deep learning, can be a little complicated. It's a little bit more math. But this book like sets you up to understand all of it when you finally get to that point. And the other thing I think is really, really cool is this, oh, I didn't realize I'm blocking this, is Kaggle. So this is the online data science competition platform site I was talking about. So companies from all over the world and organizations will post real challenges that they have and real data sets on here, and they'll post cash prizes. So you can see the Department of Homeland Security has $1.5 million in cash prizes because they actually want to find the top data scientists out there. And then this one here is another great one, $1.2 million. You can see that there's 3,780 teams are competing in this challenge from across the world. And it's really cool because it kind of gamifies it. So if you go here, they have a description of the problem, just like the data dictionary that I was talking about. They talk about different things about the data that they're supplying you with that you need to know ahead of time. The coolest thing is the leaderboard. So you can see the top people and you can submit scores every day of where we did the predictions and compared them. They give you a separate test set. So you do the predictions on that and submit them, and then they score them with the values that it should actually be. And you get a spot on this leaderboard. We can jump down, see I'm quite far down, but this is out of 3,800 teams, so this is still top 25.
That's pretty good.
I haven't submitted for 2 months, so, but it's amazing to see. So instead of getting an accuracy score where you're trying to get a higher number, this one they're doing log loss as the metric, so you're trying to minimize your loss that you have. So it's just a different function you can implement that's really easy. So you can see a lot of these people, like this is like 0.00002 difference or something, but you can go down and see that the actual difference can be just 0.001 away. So they've really optimized it, and it makes sense for these companies to invest some money in this when they can get the absolute optimal solution from thousands of different teams trying instead of just hiring a data scientist. But the other coolest part of this, because this is intimidating just to look at the data and just jump in. So the other cool part I like about Kaggle is there's this kernel sections where anyone can post their solutions. So you can actually jump in. You can see there's some in R, some in Python. And you can see right away how someone's doing their solutions. So they're importing some different libraries. They're doing a lot. And the first time I'd see this stuff, I'd have no idea what they're doing. So I'd start to Google it. But then this is actually all code you can actually copy and paste and use as your baseline, and you can start tweaking this. You can see what other data scientists are doing. You can start taking other people's solutions and combining them or adding your own flair to it, seeing if you can get more out of it. And it's cool that so many people will post these different things. I'm trying to find an easy one. Post their solutions and there's comments. Like, it really is a community where everyone's trying to help each other, and that's what makes it a great companion to studying that book. Because if you're going through the book and getting kind of a bit of an understanding, then you're looking at how people actually apply these techniques and these learnings, and it's in a gamified way and it's for real problems. It's really cool, and I find it to be easier to learn than if you just sat there with a textbook to, while learning from the textbook, go and play with some of this code from Kaggle. You can just copy and paste it to start tweaking little bits, maybe throw in a few different algorithms and try them to see different scores. And it's a great way to get an idea of the coding side and the theory side of things. So they're using R instead, but this is a nice notebook where some people write these amazing descriptions, and this one's just called a very extensive Zillow exploratory analysis. So they're actually doing a huge analysis. So this kind of is nice because you can skip some of the stuff, you can see what they've done, but they're doing this in detailed thing. That gives you a nice idea of what you should do next, because you probably wouldn't say off the top of your head, oh, I'm going to make a heat map and know how to do that right away. So being able to see how people would do it and see 4 different problems and different styles of data sets, how people go about solving them is really valuable, because these are top engineers out here. These are people that then, like, the people in the top 10 usually get hired at Google or Facebook just from this competition because they are killer data scientists. But I think it's just an amazing platform to really get an idea of diving into data science and machine learning. So I think that covered everything that I wanted to. If you search Dexter Fitchuk on GitHub, you can actually find this whole repository, and in it I put a PDF of the slides. I should mention I might add a README too and put the book and the Kaggle a link for that. But this code I think is enough to actually give you a starting point if you want to at home play around with both the Titanic stuff. Look at some of the other code here. This diabetes data set is a really cool file, and I actually have the starter version of it where, wait for it to load, where I read in the data and I set the X and the Y for you. And then in between is where you'd like add more cells, you do your cleaning, you do your training and things like that. But that pretty much sums up this packed hour and a half of talking, and I'd love to take any questions that you guys have.
So what differentiate those competitors in first 25? I mean, the algorithm they use, or what?
It can be the algorithm. Sometimes they'll there's this thing called ensembling, where they'll combine 20 different algorithms and then do like weighted outputs of those predictions and combine them. It can be different for every competition what people do, but it can be sometimes just finding those optimal parameters from hundreds of them. So it's very ambitious to try to score in like the top 10%, but it's really just a great way to start seeing how people go about solving these problems. And I don't go on it just to try and get like the top score. I know that I won't, especially because a few months ago I was number 1 on one of them, and then you wait 1 month and you'll drop down to like be in the 75th percentile or the like lowest 75%. So it's really easy to get knocked down. So sometimes it is just like changing the littlest parameter by like 0.003 or something like that. A lot of winners write really nice pieces on Medium about their solution and what they actually did. So if you are interested in all the analysis and the stuff that they did, I find a lot of really cool write-ups afterwards that they just want to share their solution. So it's different for everyone though. If I had the answer, I'd have a lot of money.
Are these supervised learning competition or no?
Yeah, most of them are supervised learning because they're trying, like this one's pretty easy. They're trying to predict home value. So they have the value of the house as the output for their training data. I haven't really seen many unsupervised things on here because for the most part, you can't really, for unsupervised, give an easy metric afterwards if you have high accuracy or not, because say you were just trying to cluster groups together, you actually have to do a lot of investigation afterwards to see if it actually would belong to a class, and then afterwards assign classes and do that. So almost everything I see on here is supervised. But that being said, like I haven't done this passenger screening one because its data set is like 20 gigabytes of image scans, like full body scans that are heat mapped. So just to download that and run it on my system, I don't have enough power for that, but then to even take all those images in and combine them into different formats, because to turn an image into numerical data can be really weird. You usually turn it into like a 3D matrix of the RGB values, the color values, and then you have to divide that by 255 to get it so it's between 0 and 1, and then there's all other kinds of weird things. So some of these ones, even though they're supervised, are really intimidating, but some of them are really nice and clean where you will just have a table. Sometimes you'll have to join multiple CSVs together on a certain column, but it's really nice too just to look at people's pre-processing code and how they make their final like data frame, like combining all the files before they actually dive into it. Yeah. I hope that I haven't confused people too much, but I hope that this has opened up you to a little bit of machine learning and how it can be a lot at first, but it actually can be really easy step by step, breaking it apart and building a machine learning solution without having a huge background of the math. And that's why I tried to, in this, include as much readable code. So if you wanted find a different CSV for something, it's called the Pima Indian diabetes data set is a really great one because it's very similar, but it has it doesn't actually have any text data. It's all numerical, which makes it even easier. But then you're predicting the same thing, a binary value, if they survive or not, if they survive, if they have diabetes or not. Another morbid data set, but it serves as a really great practice one I found.
So how do they evaluate the results? Yeah, if it's a big sample, yeah.
Yeah, so they'll give you a huge training set, and then they'll give you another data set that is everything except the output label. So then you make a prediction on that, but then you can't train it, you don't know what it actually is, so you can't include that in your training. So you submit your predictions on this other data set that they give you, and then they have the actual output it should be. So just like we did the accuracy score where we compare what we know it should be with our predictions, we don't get what it should be, we just have our predictions, and when you submit it, you'll get that score on the leaderboard, and that's actually what your score is. Yeah, so it can be a little frustrating as well, because maybe your code on your little test set that you made is performing great, but then here it's a different style test set, so you need to come up with different ways of samples. So that's where if you do that cross-validation where you would train an algorithm maybe 3 times on a different sample of your data set and then average those, you get a more generalized idea that would be more similar from what I've seen to the score you get on here, instead of assuming your one split of data would be perfect. Yeah. Any other questions? Cool. Well, most of you can follow me on GitHub, or if you find me on LinkedIn or anything, if any of you have questions or you just want an idea of more resources or something that you are interested in, if this is something you'd like to pursue or play with a little bit, I'd love to give advice, because when I was learning it, had no mentor to help me, and it was really, really confusing, even just figuring out that X and Y encode as your input and output variables. So I would love to help you. If you have any questions at all, feel free to reach out to me. Yeah, thank you very much for coming.